Seeing the invisible, or all the light we find a way to see. Your success criteria are the things that I give you to judge yourself on how well you did with a lesson. And your success criteria for this online lesson is I will describe some characteristics of the forms of light so I can then use that knowledge to understand how scientists use light to study the universe. So first understand what are some characteristics about light, and then use that to understand how scientists understand the universe and how they interpret the universe. And it's all about light with astronomy. Astronomy is the study of light from space. Nothing is going to reach us other than light from distant galaxies or distant stars. Nothing travels fast enough. So light's the only thing that we can see to help us better understand what's out there in the universe and how the universe works, but also what does that tell us about the past and the present and the future of our own solar system and our own planet. Here goes a chart of the electromagnetic spectrum. A spectrum is just the wide range of things that are related to each other. So these are all different kinds of light. And on this end, with very long wavelengths, that could be kilometers long, are radio waves, and then microwaves are a little bit shorter than that. Infrared, shorter than that. Visible light is in the nanometers, and they are so short that they can fit into our eyes so that we can interpret that and see things. And you have ultraviolet, which have wavelengths that are shorter than what we can see. And we have X-rays, which are even shorter, and gamma rays, which are even shorter than that. Electromagnetic spectrum facts. All of the electromagnetic spectrum is light. So if we go back up here, all of these are different types of light. And there are different names that kind of get used interchangeably, but they don't mean exactly the same thing, but all we're referring to light in different ways. So electromagnetic radiation, light, EMR, electromagnetic radiation, EMS, or electromagnetic spectrum. All of those things refer to light. Periodically throughout this video, I'm going to ask you some questions. And when I ask you a question, pause the video, try and answer it, and then after you unpause it, I'll either give you the answer or tell you that we'll talk about it in class. So make sure you pause the video first, then try and answer it. That way your brain will start thinking about the information, and even if you were wrong, you're going to be the only one that knew you were wrong, so you don't have to worry about that. And you can just write down the correct answer afterwards. So, question 1. Radio waves are in the electromagnetic spectrum. Then are radio waves light, or are they sound waves? Pause. The answer is that they are light waves, without a doubt. Now, what radio stations do is they encode that sound on the light waves and then send those light waves out through the city and to your car or to your home, and then your radio that you have in your house or your car translates those radio waves or those light waves and reads the encoded sound off of them and then plays them on the speakers. So, radio waves are light waves. The reason why we can quote-unquote see other parts of the electromagnetic radiation or electromagnetic spectrum is that we have tools that convert those invisible things that are still types of light or electromagnetic radiation, but our eyes cannot see them. So if you remember from the lab, the infrared camera took something that we could not see with our eyes. We had to use our hands and our sense of touch to feel the difference between the cold side and the hot side of the pan. But as soon as we got the infrared camera over there, we were able to see, quote unquote, the infrared light. And so what the camera did was converted the infrared information, infrared light, into visible light, into these colors that we could see, so that we can then see the infrared light. Because all we can see is the visible, from the red to the violet. Everything else we can't see, so we have to use tools like X-ray machines to convert X-rays into visible light so we can see them. Everything travels at the speed of light. So all the EMR, from radio waves to gamma rays, travel at the speed of light. Doesn't matter which one. Since EMR or light travels at the same speed, what is different about the types of EMR? Use this diagram to help you answer that question. So go back up here, look at all of this diagram and try and figure out the answer to this question. Use this format, I think, because the because part is the evidence that you pull out of this chart. Pause the video and I'll come back with the answer. So the answer is wavelength and frequency can be different about the different forms of light, or the different EMR. So wavelength is the distance between two light waves. So between here and here is a measurement of a wavelength. They can be short or they can be long. And then the frequency is how many waves pass by per second. So if this is my point over here that the waves are passing by, this is a higher frequency, so each of these waves is going to pass by in the same amount of time that each of these waves does. So you're going to have a higher frequency, more waves passing by than these waves, which are less waves passing by in the same amount of time. And so what is that? Like, where did that come from? So the speed of light is constant. It's always the speed of light. And so the speed of light equals frequency times wavelength. And here goes the equation for wavelength and the equation for frequency. But if you don't remember all of those equations, that's okay. What you do need to remember, though, is because the speed of light is constant, if one of these changes, the other has to change, and they have to change in the opposite direction. So there's an inverse or indirect relationship between wavelength and frequency. So when wavelength goes up, frequency goes down. And when frequency goes up, wavelength goes down. So they are the opposites of each other. But frequency and energy are directly related, or they are equivalent. So when one goes up, there's a direct relationship. So when frequency goes up, so does energy. When frequency goes down, energy goes down also. So higher frequency, higher energy. Lower frequency, lower energy. And so I put this information on the chart. You should add it to your chart in your notes. So over here we have radio waves, and they have lower energy, lower frequency, and a longer wavelength. And over here on the gamma radiation end, we have higher energy, higher frequency, and shorter wavelength. And they increase from here to here. So infrared and visible are towards the middle, and you have radio waves over here and gamma rays over here. Questions 3 and 4. Which EMR has more energy, microwaves or UV light? Explain to me why. And then the fourth one, what color of light has the least energy? So what color of visible light has the least energy? So the lights that we can see, which one has the least? I'm going to tell you the answer later. Telescopes. What we usually think of when we think about how we see into space. So this is probably the most famous observatory in Denver. It is a refracting telescope, which means the light gets bent by lenses like eyeglasses. So you have a lens here at the beginning, a lens here at the end. Sometimes there's more in the middle, but usually it's just these two, and you can move them around to focus them. But they refract or bend the light in order to be able to focus them so that you can see farther. This is me and my son a few years ago in Italy visiting Galileo's telescopes. On the plus side, they're easy to maintain. They have few moving parts, which is why they're easy to maintain. They're relatively simple design, just have some glass here that can focus. But the images aren't so great. They're good, but they're not as sharp as the other type of telescope, which is a reflecting telescope. So from the name, reflecting means that it reflects. So instead of just having a glass that focuses here and here, you have a mirror here and then another mirror here, so it reflects the light here, reflects the light here, and one little focusing eyepiece of glass here to help you focus. And yeah, the plus side is that they are clearer, more detailed images. They're actually cheaper to make because mirrors are cheaper than glass, go figure. They have moving parts though, and because they have moving parts, lots of moving parts, they're more difficult to maintain. So on some of them this is fixed, but some of them this can move, and this definitely moves around, and this part moves, and then there are some pieces here that can move around, and so they're a little more difficult to maintain. This is probably one of the more famous reflecting telescopes, and it's the Hubble Space Telescope, which was launched when I was a little kid and is still up in space giving us pictures. They've been repairing it, but it's been up there for a while, and it's still going strong. Seeing the EM spectrum can be tricky sometimes. So we have telescopes which help us see. But part of the problem is that our telescopes that we have don't always pick up all the different types of EMR that are out there. So distant stars and galaxies emit all kinds of EMR, not just visible light. And making it more tricky is that lots of EMR is blocked by Earth's atmosphere, which is really great for you and me and other living things because UV, X-rays, and gamma rays can be very damaging to us, and so the Earth's atmosphere blocks them out, making it safer for us to live here on Earth. But it also makes it trickier to see all of those different types of light if we want to study more about stars. So scientists worked a way around that, and that is by putting some of those telescopes in space. And so you have space-based telescopes that pick up infrared, because infrared gets blocked by the Earth's atmosphere. It makes a little bit further in. If this is outer space up here, it makes it a little bit into the atmosphere, but not even to the tops of our mountains. Visible light makes its way through, but we also have some space telescopes for that. X-rays and gamma rays don't really make it through, and we have different types of spacecraft that have telescopes on them that see things. Radio waves are huge, so making a huge spacecraft doesn't really make a lot of sense. So instead, we make radio telescopes on the ground. And so the light and radio waves can be picked up on the surface of the Earth, so we use it. Scientists do it that way. If you're in charge of NASA, would you fund a new space-based or ground-based telescope, and why? And would you make it reflecting or refracting, and why? Pause the video, and don't worry about being wrong, because there's no right or wrong answer to this. Just give a reason to why you would do it one way or the other, and then I'll show you what NASA decided. In recent years, NASA has been building lots of space-based and reflecting telescopes. There's a brand new one going up in the next couple of years called the James Webb Telescope. And it will be space-based and reflecting. So, yeah, that's what NASA's doing, but whatever you chose is okay too.